Okay. So right now you should be working on the lazy programming in Haskell assignment. A couple of things on that. There were some questions posted on Piazza. Take a look at those. But there was also a note that I posted on Piazza just as a suggestion. Many of you have been using filter, which is a right way to think about the list. Filter will work, list comprehension will work, all those are good ways to do it. But many are filtering the list and to test for divisibility, then calling length on that list and seeing if the length is 0. Length will compute the length of a list. There's no lazy way to evaluate the length of a list. You have to actually go through and generate the full list to then have a number to compare to 0. And so that comparison can't be lazy. You're forcing it to actually make a comparison and return true or false. So doing it that way forces evaluation of the entire list. So if you do things like filtering a list where you're testing for divisibility, what it's going to do is it will test to see if 2 divides n, and then if 3 divides n, and then let's take the primes fast case, then if 5 divides n, and then if 7 divides n, and then if 11 divides n, even if you find that the first thing is divisible by something much earlier. Okay? It will find, by coding it that way, you're in essence saying, find everything that divides n, and then see if the length of that list is 0. So that ends up being very inefficient with that. A much better way is to just see if the length of the, or rather than computing length and seeing if it's 0, there's a null function that's basically like the empty question mark in Racket. That will be lazy because as soon as you pass that unevaluated list, the result of the filter, as soon as you pass that to null, as soon as it can tell, it will stop generating the rest of the list. And it's really easy to determine if a list is empty or not. And you just look to see if it's a null pointer. There is also another predicate called any that's useful. Any kind of works like ORMAP in, actually really does work like ORMAP in Racket, in the sense that it would, you can just say any and then some predicate and then a list, and it will tell you, does any element of the list satisfy that predicate? So it's short-circuited the same way ORMAP does. So as soon as you find one that divides it, it will stop and return true. To know that it's prime, yes, you're going to have to divide all those things, but all the composite numbers that you're testing, you really want to short-circuit that as fast as possible. So if you're seeing things taking a lot longer, that's potentially why. Does that make sense? Okay, so try to avoid seeing if the length of a lazily defined list is 0. Use null or any. Use null and filter, or sorry, filter and then null or any would do it. There's a couple other ways to also test for that. You could do things like taking one from it and seeing if that gives you an empty list. That will force evaluation, but only of that first thing, because all you really care about is there a first thing that divides it or not. Does that make sense? Any other questions on the lazy programming assignment? Anything else you're running into? Some people have asked about, is the fast version that much faster? And I don't know if it was one of you, and in this section of the other one, posted actually some benchmarks. It's so fast, it's a blink of an eye, until you start getting into really, really large numbers. And so there were some benchmarks that showed that, yes, it actually does go faster if you're doing a large number of prime numbers that you're generating. Technically, it's faster even if it's, well, it's big O faster or more efficient, but it might actually involve a little more of extra overhead for small n. But you actually start seeing that effect early, but it's not
list of prime numbers, or does it calculate that as it goes?
Well, you're generating the primes fast list and then using it in his prime. And so the primes fast list is memoized as it goes through. So it's reusing elements of the list that it's already generated. Or one way of thinking of it is filter is sort of filter is sort of lazily deferred computation, and then as you start consuming more and more things from the list, it starts forcing it to filter more and more things within its prime fast predicate. And then each of those are tacked onto the list. So it actually, think of it as a list that ends in a promise or a computational lazy evaluation. Okay. Any other questions? All right. By the way, on it, there's not explicit timing requirements. We're not going to benchmark it. The main thing is just avoid needless computation of things like the entire list of all things that we might add, as opposed to seeing if any of them might add. All right, unless you have any other questions about that one, let's get back to type systems and type checking. Oh, one other thing with this. The type checker assignment, we haven't yet gotten to everything about how to do it. We're going to start on that today, but and then wrap that up on Friday. And so I hadn't actually gone through yet and posted the revised version. So I did go ahead and do that yesterday. Some of you may have tried getting a jump start on that one, which is great. It's just I didn't have the Julia 1.0 compatible shell ready to go. So that's ready to go now. Okay, so once we finish today, you should have enough to maybe just get started a little bit, and then we're going to talk more about it on Friday. All right, let's talk then about, go back to type checking. So we were talking about this idea of checking types, which is avoiding misuse of bits. So remember that we encode things in binary and we write it to memory locations. We need to be absolutely certain that we're pulling it back out and interpreting those bits the same way that they were intended when they were written. And that's in essence type checking. To do this, you can either do this dynamically on the fly, but you have to store some little extra metadata. So you basically store, instead of storing a raw int, you store a little wrapper around it that says, hey, this is an int, and inside is the actual contents. And you do that for every type. You'll have a little wrapper with a header that says, this is what type this thing is, and how to interpret the main payload bits. You check that at runtime, and so we talked about how you store that extra information, you check it at runtime. It means you don't find out errors until runtime, but it also means that the type system's not nagging you until runtime. This is actually really, really easy to implement, and we already did some of it in our interpreter so far. There are advantages, though, to do it statically, like in C++ or Java, where it ensures that types are being used correctly at the beginning of the execution. So either compile time or before you actually start running the program in interpreted languages. We went through advantages. Some of these are, it catches errors before you ever ship the program, launch the missile, whatever the system is. You know that there aren't type errors, at least for the type errors that that language catches, which is not always all of them for some languages. You know that any errors that you're going to get that way that it will catch, it will let you know about beforehand when you compile. It also avoids all the runtime overhead of the checks, plus there's other kinds of optimizations that you can do if you actually know the type of everything ahead of time, especially during compilation. So we got to this question last time at the end about, can we always do that? Given that there are advantages to doing static type checking, is it always possible? We looked at an example like this, an equivalent in C, where It's possible to know statically what the type what type this expression will return, because it could return a number, it could return a string, and I won't know until runtime what the value of x is. Now there might be trivial cases where I know what x is, and then maybe I can determine it. It's also entirely possible that if this is inside some much bigger set of code, the rest of that code, based on what x is, will use the result of this as a number or a string. So I can't determine what type it is, but that may or may not actually result in an error. It's just I can't determine it for sure. And so this leads to a trade-off, and it's a fundamental trade-off when you're working with static types checking. There's over-approximation, which says, if I cannot determine what the type of this is, I'm going and absolutely determine that there won't be a type error, I'm going to reject it, give an error, because there might be a type error. Okay? So this is the ultra-conservative approach. I can't determine what it is, therefore it might be a type error, and I'm going to reject it. There's the under-approximation, which is I can't tell what this is, whether this will or won't cause a type error, and so I'm just going to let it through and let it be on the programmer. And so you kind of have this trade-off. It means that you get less security as a programmer of knowing that it's going to catch type errors in the under-approximation case, but the type system can perhaps be a little overly finicky if it's over-approximating. And again, you have to try to balance between these two. Right, so how can you try to do it? Well, one way is get more information if possible. So you can try to get more information. One is have the programmer tell you. Right? So there's manifest typing that we talked about before, which says I'm going to declare the type of every variable, I'm going to declare the return type of every function, the input type of every parameter, and so on. That can be a lot of extra work for the programmer, just to make the type system work a little easier. Another is you can actually try to spend a lot more, I'm going to jump to this third point here. You can also spend more computation to try to figure it out. You can do what's called type inference, that we're going to get into in a little bit, where I can actually work harder to figure out the type of everything. Even then, there might be some I can't figure out. And so there are some systems that they don't require you to declare the type of everything most of the time. So in other words, I'll work harder as the compiler to try to figure out what the type of everything is, rather than just having you declare it. Except in a few cases, I might give you an error message that says, I can't determine what this is, give me a hint. Okay? And then ask the programmer to declare a little bit more. The other case, and we touched on this last time, is literally cripple the language. Now that sounds bad, and it sometimes is, but it's a very common choice. So if the problem here is the if or the then and the else branches return different things, just don't allow that. So many languages that have constructs like this will require that everything that's returned be the same type. Whether it's the then or the else branch of an if, whether it is, and we saw that C actually does that, C++, whether it's multiple different return statements that are inside of the same function. Even if you don't declare what the return type is of the function, you can require that all the different values that that function returns must be of the same type. So these are restrictions that you actually put on the language itself to make the type system work. So if it's a construct in the language that makes it impossible to determine types for that particular construct, instead of going the over-approximation, under-approximation route, you just simply don't go there and just say, I'm not going to allow that in my language. So in our type checker, that's actually what we're going to do. We'll introduce a requirement that the then and the else branches return the same type. Now it turns out that's usually not a super big restriction on a programmer, but be aware you are actually imposing some restriction on that. You see the idea? Now, it turns out that even after all this, there still may be some things that you can't check. So let me give you some examples. Accessing, and I showed something like this last time, accessing the 11th element of a 10-element array is a type error. But if the programmer just says A sub I, and up here earlier, I know that there's some integer I, but there's a whole bunch of other code that's happening in between. Is that or is that not going to be a type error? And the problem is you don't know, because you may not know until runtime what the value of the variable I is by the time you get to this point. So you don't know if that array index operation is going to exceed the bounds of the array. So exceeding the bounds of an array is a type error. It will cause you to read elements of memory that are not what was coded that way. Or another way of thinking of it is if you think about sort of illegal operations, accessing the 11th element of a 10-element thing is an illegal operation. It's a type error. So what does C++ do with this? What kind of type checking does C++ do with this? Turns out not even quite dynamic for C++. C++ just says, I can't check that. You're on your own. And so it will access that 11th element of memory, or it will access the memory where the 11th element of the array should be, okay? Whether it was intended to be encoded that way or not. Okay. But what does Java do? Well, so by the way, in C++, this will not cause a compile time error, and it, in all likelihood, will cause, well, sorry. If you're lucky, it won't cause a runtime error, but it might. Okay? So a type error can actually occur. What about Java, though? Will Java complain about that at compile time? Not quite, yeah.
Doesn't it throw an index out of bounds exception?
Yeah, but when does it throw it?
Runtime.
At runtime. So at compile time, Java is still, just like C++, can't determine what the value of that variable is going to be. So it cannot give an array out of bounds error at compile time. For trivial cases, I think constants that are defined bigger than the array bounds, like, you know, you can check it. But if it's an actual variable that could take on any value, you can't statically check that. So, but Java still actually will trap the type error. It won't let you commit the type error by reading outside the bounds of that array, but it does it at runtime. It throws a runtime exception, not a compile time error. In other words, it's doing static type checking, but it's injecting a little bit of dynamic checking in there as well. You see the idea? Now, and it can do that because every array, as part of its data, the allocation, you guys know arrays are allocated on the heap in Java. We talked about how things allocated in the heap have a header. And in Java, quite often that header will include type information. Well, for arrays, part of that type information is how big is the array. And so Java will actually, the Java virtual machine will actually check that at runtime and make sure that you don't exceed the bounds of the array. What about the following? In Java, actually, yeah, in Java you can take, so suppose I have class A and I have a child class B. Now I can have a variable that's of class A store an object of type B, right? Class B. But I can also then say, I can only in that case treat it as an object of class A. It has an explicit operation to do to downcast it to a class B. Now, what if actually there's another child class C and it really belongs to that class instead of class B? What will Java do? Have you ever done something where you're maybe having an array or something else of some other data structure of a parent class, and then you actually downcast it to whatever its actual correct class is? So Java allows that. If you do it right, works just fine. If you do it wrong, it will actually catch that error. You can't, if you have class B and C that are both derived from class A, you can't downcast something that's of class C to class B. It will say runtime exception, throw an error, or throw the exception and then you have to catch it and deal with it. So again, Java does static type checking, but it injects a little bit of dynamic checking in there as well for things that can't be statically type checked. Lots of other languages do this as well. Be aware, C and its variants do not. C and C++. They basically, we're going to do all the checking at compile time, zero checking at runtime, and leave that up to the user or the programmer. All right. So enough about static versus dynamic and advantages, and then can we always do static? Sometimes with a little dynamic injected in. Let's talk about how to do static type checking. The key is you first have to define what's called a type system for a language. So you've heard me use that term. You'll see that used in a lot of books, lots of other things. A type system is the rules for that language and how it uses types. So you first off have to define what are the types in the language. So what's your set of types? Ints, floats, structs, classes, objects, all these other kinds of things. Functions, is that actually a type or not? And so you define all your types. Remember, that's set of values and operations on each. And then you have to have some set of rules for figuring out when I have expressions of different kinds that have certain different kinds of types, typed things that it's using, I need to have some set of rules for determining what the type is of other things. Okay? So if I add a number and a number, what is the resulting type, right? And one of the ways we're going to frame that is we're not going to say the result of a plus is a number. We're going to say we're going to say things like if A is an int and B is an int, A plus B is an int. Otherwise, I have no rule for determining what A plus B is. And that is then taken as a type error. And then finally, you have to have some algorithm for applying the rules. So a type system, again, is three parts. What are the types in the language? What are the rules for correct use of types, and then inferring and figuring out the types of other things? And then finally, you have to have some algorithm for applying the rules. Now that algorithm can be really easy. We're going to implement one that's nothing more than a post-order tree traversal, which you should understand all those terms out of 235. But there are others where I may have to make multiple passes through. I may have to generate constraints in almost like a Prolog-ish fashion and then unify them to try to figure out what's what. So these algorithms can be very, very simple, or they can be very, very complex, depending on how complicated your type system is. So let's talk about a very simple algorithm. And this is what you're actually going to implement for the next lab. So for our interpreters, remember we take the input, we lex it, we get a string of tokens, we parse it, we get an abstract syntax tree. Right there, between parsing and calc, or in a compiler, between parsing and compiling, remember we've talked about how there's that space? You can do all kinds of stuff, optimizations, pre-processing, syntactic sugar, all that stuff. That is the niche where static type checking goes. So you want to do static type checking, right? By definition, it's static. You do it before you start running things or before compiling. But of course, you want to work on the already parsed abstract syntax tree because that's the easiest form to work with it. So we're gonna do static type checking. All static type checking is done in that niche between parsing and compilation. So let's take a simple case. Suppose we have a plus node, so we have the following expression. We're going to add 1 to the result of subtracting 3 or x from 3. So we parse this, we get a plus node that has a num node 1 for numeric literal. Actually left out a little line there. And then the second operand is a minus node with num node 3 and num node, sorry. I goofed on one thing, let me just fix this. Got a little ahead of myself on that one slide. All right, so let's suppose it's all just numeric literals. So here's the algorithm we're going to use. We're going to recursively traverse this tree and determine the type of every single leaf, every single interior node, all the way up to the root. And so we're going to determine the type of every single expression and sub-expression in the entire parse tree. Here's how you do it. So I need to know what type does a plus node return. Well, suppose we had a more complicated language where a plus node could work with ints, it could work with floats, maybe it works with string concatenation. I would need to know the input types. So let's recursively determine all the types of everything in each subtree. And well, to know that, I might have to recursively know the types of everything in those subtrees, and so on and so on. Eventually, when you get to the leaves, we'll need to know the type for everything. Right? So we're going to work with our language in a way that every leaf we will know the type of. And if I know the type of a leaf, and I have rules for determining from the leaf types what the next node up the tree is, and I have rules for knowing from that what the next node up the tree is, and so on, you can recursively determine the entire type, the types of everything in the tree. So here's the process. We're going to recurse through the tree, the AST. It's a post-order traversal. Recurse on the subtrees, then visit the current node. So we'll recursively type check and determine the types of every sub-expression. Oh, by the way, if that catches an error in a sub-expression, then we just stop. So recursively type check and determine the types of every sub-expression. Then verify that the types are being used correctly for this node. In other words, you don't have some sort of type error that's occurring at this level of the tree. And then return your type to the next level of the recursion. So here's how this would work with this. We look at plus node. We recurse on this subtree, we recurse on this subtree. Let's recurse on num node. What is, right, first off, there's no type error in a numeric literal, right? So no errors occur. And obvious question, what's the type? What type will that return at runtime? A number, right? Okay, so I know the type of this branch is a number. Also recurse on this branch, that's a minus node, all right? I'm gonna have, that has subtrees. So I'm gonna have to recurse on this one, that's a number. This one, that's a number. Number minus number is a valid operation, so we're checking at this, so we've determined the types of the children, child sub-expressions. We verified here that number minus number is a valid type operation, or validly typed operation. And if so, we know then that this returns, this minus node will return a number at runtime. We don't do the computation. All we're doing is saying, I know that at runtime this will return something of type number. And so if this is a number and this is a number, then you're back up to this level of recursion. You're verifying that number plus number is correct. Yeah, that's good. That also returns a number, and then you return number out of the recursive, the call to determining the type system, or the type of the entire sub-expression, or the entire expression. So notice the steps. It's just classic post-order tree traversal. Recurse on the children, make sure that their types are correct, and determine what their types are. 2, visit the current node, and check and make sure that types are correct. And 3, return to your caller of the recursion what the type of this sub-expression is. And that's exactly what you're going to code for the last lab. Now, one of the things that's going to happen is you'll notice the information that's being determined at each level of this tree is type information. We need to have a data structure for storing type information. In other words, if you'll pardon the sort of odd terminology, we need a type. Okay. So we will actually have a type val as part of our language. We're actually going to have something that represents types in our language, because the static type checker needs to use that. Everybody okay on this? Feel like you could implement that? Okay, let's throw a curve in. All right, so everybody okay with this recursive traversal, just post-order traversal? What if I did the following? With x defined to be 0, add 1, 2, and instead of -3, 2, -3x. You can see where I had the arrow in your slide. Does this produce a type error? Okay, so let's go through our algorithm. It's a with node. A with node has a sub-expression for the binding. That's the num node 0. And it has a sub-expression for the body. That's the +1 -3x. And you'll notice this is exactly the same as what we had before, except instead of a literal 2 down here, it's a 3. So we recurse and determine the type of this is a number. That's easy. Type of this is, oh, okay, we're going to have to recurse. Recurse here, that's a number. Back, that, oh, okay, we're going to have to recurse from there. That's a number. That is, what's the type of this sub-expression? The variable reference to x.
Should be num node.
Yeah, I mean, at runtime, what type will x be storing? A number, a num val, right? Because if you think about what's going to happen at runtime, x will be bound to 0 here, and so that when we get down to here, x will evaluate to 0, which is a number. Okay, now, if you think about our current algorithm, it has no knowledge of that. How do you know that this is going to be a number? Yeah.
It's in the environment.
Right. But the environment doesn't exist that stores this variable has this value. It doesn't exist until calc when we're doing runtime. So what could we do? Yeah.
You can just ignore it, say it works.
Okay. Now you're getting to be almost like C. Sorry. No, but that could be a type error, right? What if I actually initialize x to be some function, and I try subtracting 3 in a function? Somehow you have to get the information over here that x is being initialized with 0, which is a number, all the way back over to here. Now, the way that we did that at runtime, you're exactly right with what you said earlier. The way we know at runtime that x has the value 0 is to use an environment. Right? So you're exactly on the right track. We just need to do the same thing when we're doing type checking. We need to keep an environment during type checking that stores what variables are in scope, but we don't know their values. We won't know that until runtime. What we care about is what is their type. So we're going to build what's called a type environment. By the way, what if instead of this being an X, this is a Y? What should happen? We can actually catch the unbound variable error at type checking time. We don't have to wait until runtime to find out that it's unbound. We could tell the user right up front statically. So with a type environment, we can actually check and say, hey, Y isn't even in scope here, let alone determining what its type is. So we're going to use a type environment. And this is critical to all type checking kinds of systems, at least that use this kind of recursive approach. So we're going to store a type environment. It binds identifiers to types, not to values. So when we see something like this, we're not going to say X has the value 0. We'll type check this binding expression here, this initialization expression, and we can tell at type checking time that that is of type number, because num nodes return numbers. And we can actually then say this value, so X, I know that it is a number at type checking time. And then when I get all the way over here, you look X up, and you determine that it's a number, and then, oh, number plus number minus number is fine. That's a number. Number plus number is a number. The width just returns whatever the plus does, so the whole thing returns a number. So type environments are critical to what we're going to be implementing from this last lab. They don't store this variable has this value. They store this variable has this type. The value may depend on things at runtime. And the same way when we went through doing calc on this thing, you know how we said calc this expression with an environment that binds X to 0? We're going to type check this body expression with a type environment that says X is a number. So that whenever you run into variable references to X, you know that those will evaluate to numbers. So the structure of the code is going to look just like calc. We'll pass an expression and a type environment in, as opposed to a value storing kind of an environment. When the variable's created or defined, so this could be with a width or as formal parameters to a function. So we need to know what the types of the formal parameters are when we are type checking the body. Now that can be declared by the user, or it can be inferred from how the function's used. We're going to actually take the easier route. We're going to make the user tell us. And then when the variable's referenced, we're going to look it up in the type environment to get its type. Again, not its value, but its type. Questions about either the basic algorithm or type environments? Yeah.
So if we had the case where the varref node had a Y in it,
Yep.
we would throw that error by going into the type environment and say, oh, this variable doesn't appear, so it's
Exactly. So the same way at runtime, we'd go to look up Y and find that it has no value. It's not been defined. At type checking time, we can say, there's a reference here to something that's not defined. And we can just throw that error right away. All right, so if you go back to our definition of a type system, let's think about this for implementing our language. We have a set of types. Right now, they're num vals and closure vals, right? Or num being closure, I think we call it. Just to make it interesting, let's actually throw in one more type, and that's an explicit Boolean type. So your last lab will have one more type. We'll have numbers, Booleans, and closures, functions. We have an algorithm. We've talked about this recursive traversal through. Now, by the way, that recursive traversal one pass won't always work for all languages and all type systems. It does for simple ones like what we're building. So other things you might need more complicated algorithms, but we're just going to use a single post-order traversal of the abstract syntax tree passing along type segments. So that's our algorithm. We have types, we have algorithm. We still need to come up actually with a complete listing of all the type rules for our language. These are called type judgments. So a type judgment is a rule, think of it as a rule that lets you say, if this condition holds on this input type and this condition holds on this input, then I can say this about the result of this particular expression. Okay. So that's the general form. It's going to be if this and this and this in the context of the current type environment all hold, I can say such and such about the current operation, the current expression. Now there's a notation that is used in formal systems. You're probably not going to see this if you just pick up your average how to program in X book. But if you actually start diving seriously into understanding type systems, there's a notation that they use. I'll show you the notation, we'll write out the rules, but I'll constantly be translating into English. And the notation basically looks something like this. And if that looks like Greek to you, yes, that actually is Greek. It's the capital gamma. The way to read this is as follows. In the context of the current type environment, so we're going to denote the type environment with a capital letter gamma. In the context of the current type environment, this sort of funny sideways T here, and it should be read as, we can say that this expression results in this type. Okay. So what we're really ultimately trying to say is, remember we said that expressions will, when evaluated, will result in certain types, but it's dependent on the context of the current type environment. So a reference to an identifier X might return different types depending on what the type environment is at the time we're evaluating the X. So think about it. This is the type environment, the expression we're trying to determine the type of, and this is what it will result in. And the rest is just sort of syntax or syntactic glue. Everybody okay on this so far? All right, let's take our last, just check time here. Let's take our last few minutes and start talking about our language. Next time we'll start actually writing out rules. So for the next lab, we're going to spend all next time actually writing out the type rules that you would enforce with this. So we're going to do the following. Here is the language that you're going to process. It's built on the CI3 language. This is where you had first class functions, but we're back to just single binding widths, single binding or single parameter functions. You don't have to extend those. Oops, sorry. I need to tweak this syntax to actually match what we changed CI3 to. So I'll fix that right after class. So we're still going to have numeric literals. We're going to throw in Boolean types. So we need to have Boolean literals, true and false. We'll have simple addition, simple subtraction. You do not have to implement bin op and all that stuff. You know how to do We're just focusing on the type checking. Let's throw in some other things to actually use Booleans and do some other stuff. Is 0 will be a predicate that tests to see if something's 0 and returns true or false. Okay? So we'll take a number in, Boolean out. Notice we're already starting to get into some of the type rules. We're going to change our if. Instead of being if 0, we're going to do if b, meaning if Boolean. Remember back when I introduced if, I said there's two common approaches. One is require that the test of an if be a Boolean. That means you have to have a Boolean type, so that's what Java does. Or compare it to some value, some magical values that mean true or false, which is the C approach. So here we're going to take that first one instead of the second. We'll have a test, which would better evaluate to a Boolean, and then else parts. We're going to constrain it that those have to return the same type. But we don't care what type that is as long as they're the same. With ID binding expression, values, that's the same. Variable reference, function call. If you think about it, this body expression might reference the formal parameter. And it might need to know what the type of the formal parameter is. So how do you know what the type of the formal parameter is? There's basically two ways. One is make the programmer tell you. The other is work extra hard to look at the calling context of the call and make sure and figure out what it is by the way that things are being, by the parameters that are being passed to it. That's a lot more work. We're going to take the first one. We're going to require that the programmer tell us what the type is. So we're going to add a little extra syntax. So lambda identifier colon type, meaning the type of this formal parameter, and then the body expression. This is a function call, same as before. We're also going to add a list type to the language. So we'll have numbers, Boolean, closures, and also a numeric list type, a list only of numbers. We'll add 5 other operations for this. nEmpty returns an empty number list. nConst is, this is just const is empty first and rest for number lists. Big thing with the assignment, you do not have to implement calc for this. We give you the parser, so you don't have to do anything else to the parser. Been there, done that, you guys know how to do that. Okay? Just use the parser, you don't have to bulletproof it further. Focus just on the type checker. Notice that we're requiring the programmer to tell us what the type is. So we actually have to give them syntax for declaring types. So you've seen in Java and C++, there's a syntax for how you declare the types of certain variables. So we're introducing a new non-terminal into the grammar that's type. It's used right here and it's defined here. It will be literally writing out number, writing out Boolean, writing out nList, or we'll wrap up with this. For a function, we'll write paren, input type, colon, return type, close paren. Now the reason we need that as a valid type is what if you write a function whose input parameter is another function? Then you have to have syntax for writing the type signature of this formal parameter. So what we'll do next time is we'll pick up with this and we'll write out all of the type rules using this type judgment. We'll write out the type judgments using the notation. So you have grammar, you've seen algorithm, I'll show you the type environments more. We'll actually write out the type judgments on Friday.